Today we want to look at the final chapter in our magic of moving charges. We already learned that when charges were at rest, they felt no magnetic force. When they were moving through a magnetic field, we learned that there was a force that would cause them to deflect. That magnetic force was the product of the charge, the velocity, and the strength of the magnetic field in Tesla. We learned how to represent magnetic fields going left and right, up and down, towards us, and away from us. We learned how to use magnetic fields and the magnetic force to trap particles in a magnetic field. We learned how to use the magnetic field along with an electric field to select a velocity to come out of our velocity selector. Things that were going too slow would hit one plate, and particles that were going too fast would hit another. So we would be able to get an exact velocity of the particles coming out of our selector. We then use that in a mass spectrometer, which is one of the most important scientific devices ever designed to figure out the mass of extremely tiny objects, isotopes of different elements, molecules that are really small. We can get their mass using the mass spectrometer, and we've already learned all this. Today, what we'd like to do is close it out by learning about the magnetic field around the current carrying wire. This was first discovered in the 1820s by Hans Christian Ørsted. You may already have him on your sheet of scientists, but if you don't, make sure you put him on there. Okay, what he did is he noticed that magnetic fields are created by current carrying wires. He noticed that a wire that is carrying a current would deflect a compass needle. So here's our compass on top of a wire when there is no current flowing through the wire. And you can see the compass pointing north just like it's supposed to. But when you turn on the electricity, and electricity flows through the wire, all of a sudden, we see that our compass needle deflects, meaning that our wire is creating a magnetic field. As soon as you turn off the current, the magnetic field disappears. We did a lab where we were looking at this relationship, and we looked at how distance, which we're going to call R, and current, which obviously we use I, affect the magnetic field, which goes by the letter B and is measured in Tesla. And what we discovered were these two graphs. So make sure these graphs are part of your notes for today. And you could see that these are pretty simple relationships, maybe our two simplest relationships. They are inverse and proportional. So magnetic field, which goes by the letter B, is inversely related to distance. That means if we double our distance from the wire, the magnetic field will be cut in half. Make sure your distance is in meters and your magnetic field is in Tesla. When we look at current, again, we have magnetic fields, we have some sort of graph constant, and this time we varied the current. And we can see that it was a proportional relationship. Zero current would make zero magnetic field, and as we increase the current, we increase the magnetic field in a proportional relationship. If we were to double, so we go from 2 to 4, if we double our current, we're going to double our magnetic field. So these are the relationships that we found in lab. Again, distance is often going to go by the letter R because the magnetic field is going to be forming a circle around the wire. So again, here's our picture. This should be in your notes too. This is our R from the center of the wire to the spot where we want to find our magnetic field. And the factors again are radius and current. Our final formula looks something like this. B, magnetic field in Tesla, depends on my current in amps and my radius in meters. You'll notice we have a constant to get the units to work out right. This constant should be found on your green sheet, so look that up and write down the number in your notes. On the bottom, you'll notice we have another constant, 2 pi, and you'll notice 2 pi r is on the bottom. 2 pi r represents the circumference of that magnetic field. These magnetic fields form circular loops so that the magnetic field spreads out not in a sphere this time, but in a circular pattern. And the bottom of this equation is the circumference of that magnetic field. We can use this fact that magnetic field is generated by a current to use a contactless current meter. You simply measure the magnetic field around the wire, and we could use the formula to figure out how much current is flowing in the wire. This is a beautiful thing because we can measure current without actually having to touch the wire, without having to disconnect anything and hook up our meter. It is safe, it is quick, it is efficient, and it depends upon our formula. Magnetic field equals our constant times current over 2 pi r. We can calculate the magnetic field at a certain distance away from a wire using this formula. We tried something like this before. If you'd like to find the magnetic field at a house, you would simply plug into the equation that we just had and solve for magnetic field. These wires create such a strong magnetic field that if you take a fluorescent light and bring them near these high tension lines, the magnetic field will actually light up the fluorescent bulb. Okay, the changing of the magnetic field, since AC electricity is going through here, will actually cause the bulb to start glowing. And that's where we're going to end for today.